Okay, so it's continuation of the lecture 5. So I told you about the discontinuous gel, which has two separate gels. Top one is, I told you, staking gel. The bottom one is the resolving gel, where the main separation is taking place. So the purpose of having the staking gel on top is to have a better separation here first, and then once the proteins are separate, they will be able to go into your high percentage resolving gel much better, easier way. So you're not going to have any bottleneck here. So that is the whole purpose of having a top small stacking gel. Okay. So typically you have the stacking gel on the top and the bottom gel is a resolving gel. So and then your gel setup is this way. There's a one metal wire on the top, another metal wire at the bottom. So the top one is the negative charge, of course. Bottom one is the positive charge. Your protein will migrate from negative to positive. That's how it's done. The glycine buffer. Okay, normally glycine is used as an electrolyte. So again, sticking gel about 5% gel, and the bottom resolving gel is 10 to maybe 15% gel. So that's what I mean, the percentage difference. Okay. So your protein is denatured. Typically, you normally add your sample loading dye, which contains sodium dodecyl sulfate, SDS. And after you mixing your proteins with SDS sample loading dye, you normally boil it at a high temperature. So during that boiling, the proteins stick through hydrophobic interaction, because high temperature will unfold your protein a little bit. So the hydrophobic residues are exposed, and your SDS can bind with them easily. Okay, so once SDS binds, it presents that uniform negative charge, because SDS had SO minus, it gives that uniform negative charge. Okay, so after adding SDS, your protein's charge is disregarded. And then you also add, like I told you, beta-mercaptan or dithiothionitol to dissolve the disulfide bonds between cysteines in your protein. Okay, so this is what SDS, SDS does, of course. SDS is binding with your protein through hydrophobic interaction, and you have the negative charge now. And then disulfide bridges between two cysteines are broken through beta-mercaptan and or dithiothionitol, I told you. And the size determination, your proteins, you have to have a molecular weight size marker, size standards, right? You can buy these. Okay, so already known proteins are mixed up, and you can compare the size of your proteins against them. For example, this size standard marker contains these many proteins, and the size of those proteins already known. For example, myosin protein is about 200 kilodalton size, and the smallest protein, lysozyme, is about only 14 kilodalton. In between, there are so many of these proteins that are pure, and their size is already known, so they will show up on these locations of your gel. And if your protein sample is located somewhere in between, you can compare your protein's location to the proteins shown up in the size marker. So this band has 45 kilodalton size. That band has about 31 kilodalton size. Then your estimation of your protein size would be what? About 36 or 37 kilodalton. Okay, that's how you can estimate your size. Of course, you can also plot, your standard curve using your, size standard, of course. So, their sizes versus migration distance, okay, from here to wherever they are, and then that'll be linear. Actually, it's exponential. So you may want to use log for your size, protein size. Then you can see the linear line. You can get the equation, R-square value, plug in migration distance for your protein. You can estimate the size mathematically if you want to. Okay. And the acrylamide gel, it is made up with polyacrylamides, multiple acrylamide. One is regular acrylamide, and the other one is called bis-acrylamide. So by cross-linking two acrylamide, you make this polyacrylamide network, gel mesh. Okay, so when you make this cross-linking, of course, you need to add ammonium persulfate and timid, which will generate a lot of hydroxyl superoxide the hydroxyl radicals, and they help the polymerization process. So this is important if you are asked to make your own gel, but these days people do not make their own gel because gels are so cheaply sold by companies. So, but you know, when I was doing my research, I had to make my own gel, so I had to mix these chemicals together, and these two chemicals are very neurotoxic, so you don't want to mess up with them. So it's better not to make your own gel and just buy them. Okay. So the ratio of those polyacrylamide bis versus acrylamide is normally 1 to 20 or 1 to 29, depends on the percentage. Okay. So of course, the higher the percentage is, okay, in your gel, the polyacrylamide percentage, your pores will be smaller, right? So 4% gel, so up to like 12% gel you can use with the ratio 19:1 ratio of, you know, bis normal versus bisacrylamide. You can also make you know, these percentage with the higher normal versus bis polyacrylamide ratio. Anyway, and the higher the percentage of the overall polyacrylamide gel is, the pore will be smaller, so they'll be better to separate out proteins that are small and they are similar in their sizes, of course, right? And the lower the polyacrylamide percentage, they'll have large size pores, so it's better and easier to separate out large protein molecules. So that's the principle. Okay. You can also use polyacrylamide gel to separate out your DNA and RNA molecules because they will give you better resolution. Actually, DNA sequencing gel is run on acrylamide gel instead of agarose gel. Okay, so you can separate out DNA molecules that have only like one nucleotide base pair difference. You can do that. So yeah, DNA is also run on polyacrylamide gel. And then we talked about SDS. You normally prepare as a stock solution of 10%. You delete it from there. Timid APS solution, I told you if you're making your own gel, those are needed. But these days, nobody's making their own gel. And then electrophoresis buffer normally contains tris and glycine. And glycine is the electrolyte. So you have higher percentage of glycine, 250 millimole. And then little bit of SDS, 0.1%, at the pH 8.3, little basic. You adjust that with your tris. Okay, tris is a base, but you add a little bit of acid to bring down the pH, of course. And that is the electrophoresis buffer. So the main two things here in this buffer is what? SDS. Okay, that's going to be a strong denaturing, and glycine is an electrolyte. It carries your protein through the electric current. Now, sample loading buffer, the purpose of this is what? You mix your proteins with sample loading buffer because sample loading buffer has the SDS. Okay, so the same volume of your protein is mixed up with the same volume of your sample loading buffer. Okay, when you do that, you will make SDS concentration 0.1%, same as this. Okay, and then it contains DTT, dithioterephthal, to dissolve those disulfide bonds between the cysteines, right? And the rest of them are what? Tris buffer, it's a buffer, and the bromophenol blue is what? It's a blue color dye, so it gives the color so you can see where your sample is loaded to the well, and when it goes into the gel you can see the movement of your proteins. And the glycerol is added for what purpose? Glycerol is a heavy, dense molecule. So when it's mixed up with your protein samples, it makes them heavy. So when you load it to your gel, your sample will be settled down at the bottom of your well instead of floating it out. Okay, that's the purpose of adding glycerol. So sample preparation again, about 50 to 100 total proteins are needed for you to have very visible protein band showing up on your gel. So it's mixed well with the 2x SDS sample loading buffer, about 1:1 volume ratio. And then it's heated at the water boiling temperature of 100 degrees Celsius for 3 to 5 minutes. During that time, what happens? Your protein is denatured a little bit. It's exposing its hydrophobic parts, and it's binding with the SDS, the hydrophobic parts of SDS. So SDS is well coating your protein. That's how you prepare your sample. And once that's done, your sample is ready to be loaded on your gel. So your gel should be set up on the electrophoresis container. Okay. So again, this shows you gel preparation process. You don't have to do that because you're not making your gel. This is gel pouring and solidifying and preparing stacking gel, all those things. But hopefully you don't have to do that. And you just set up your gel and load your sample and run your gel through the electric current. Once the gel running is done, you have to visualize your protein samples. Because your protein samples are not visible, you have to stain the entire gel. So there are a couple of staining methods that you can use. One is called Comasi beryllium blue staining. So if you use Comasi blue staining solution, which has about 0.2% Comasi beryllium blue dye, blue dye solution, and then it's dissolved and mixed up with methanol and water and acetic acid, 45 to 45 to 1 ratio of the solution, then you'll have a very dark blue solution. So you submerge your gel, entire gel, into this solution and let it soak up the Comasi blue inside of this solution. Okay. Once you leave it in that solution about 4 hours on a shaker incubator, then you will get to see your entire gel will be stained with the dark blue color. And then that's not the end of it, because everything will be blue at that point. Then you have to de-stain your gel by moving your gel from this staining solution to a de-staining solution. The difference is de-staining solution doesn't have Comasi blue. Instead, it's made up with methanol, water, and acetic acid. Okay, so it'll remove the Comasi blue from your gel. But when you do that, the gel will lose Comasi blue much faster than your proteins. So your protein will have dye stuck with them, but your gel will lose Comasi blue. That's the time when you stop the de-staining. Okay, then you will see your protein band showing up on the gel that became transparent. Okay, so that's how it works. So staining first, and then de-staining. De-staining normally takes about a long time, 4 to 8 hours. Times 3 or 4 times. So it's normally done overnight. Okay. Once you do that, you will see a gel like that. See, the entire gel is kind of transparent, but your proteins are still showing that blue color. So you'll see the stack of all those protein bands showing up, the size marker there. Okay, that's the Comasi blue stained STS page gel, typically looking like that. Okay. And then the other staining method you can use is called silver staining method, because it uses silver nitrate in its staining. The benefit of using this method is silver nitrate has much higher sensitivity, meaning it can detect small amount of proteins. Like typically 0.1 to 1 nanogram of protein can be visualized as a band. On the other side, Comasi blue, what did it say? You have to have about how much? It was said, yeah, 50 to 100 microgram total. So yeah, silver staining method is much better because you don't need a lot of proteins, only 0.1 to 1 nanogram. That's fine. Okay, but it takes a long time to go through the staining method. So fixation, first step with the ethanol, glacial acid, and water, 4 to 12 hours, and then 30% ethanol incubation for 30 minutes, and then you have to add silver nitrate for 30 minutes staining, and then wash with water, and then you have to incubate with developing solution made up with 0.2% sodium bicarbonate and 0.02% formaldehyde. It's toxic. And then you develop that. Development process is quenched with 1% acetic acid solution. So it takes a long time, although it's more sensitive. And once it's stained, it looks like that. Okay, it's stained gel. You see a kind of dark yellowish brown color of proteins from your silver stained gel. Okay, understand the pros and cons of 2 different gel staining methods.